Carlos Plain, a professor at Durham College, said that the James Webb Space Telescope is questioning a lot of the cosmological truths that have been accepted in recent years. I have dedicated my life to cultivating a particular theory about the universe, and now the theory is being tested. I am happy about that because that is how we advance. That is how we make progress in science. Another ultra-deep image highlights our cosmological errors. Now operating against historical context, the telescope that was meant to unveil the universe's first stars may open up a whole new area of research. Not all analysts are trembling in dread at the new findings. Many academicians are happy with the results since they have long been certain that something was wrong with our earlier hypotheses. Even though the disparities in estimations of the expanding pace of the cosmos should have broken the conscience of scientists long ago, they continued to adhere to their outdated beliefs when it came to accurately grasping the warnings. The cosmic microwave background radiation, CMB, considered the most well-established light in the universe, was produced approximately 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to unite to form stable hydrogen particles. This process, known to scientists as reionization, made it possible for light to enter the cosmos. The CMB was discovered in 1964 by American scientists Robert Wilson and Arno Penzias as they were developing a novel type of radio antenna technology. Penzias and Wilson's discovery, which won them a Nobel Prize and cemented their place in astronomy history, was long regarded as one of the strongest arguments in favor of the Big Bang idea. The CMB most likely offers a glimpse into the early universe, as minute variations in temperature provide crucial details about the circumstances immediately following the Big Bang. Among other things, scientists utilize the CMB as a physical record of the basic measurements of the material world to calculate the universe's pace of expansion. This was originally proved in the late 1920s by the astronomer Edwin Hubble, who found that the speed of distant cosmic systems varies with their distance from us and that they travel away in all directions. These findings are now known as the Hubble regulation or the Hubble steady. Because Hubble lacked the high-level estimation capabilities that were available several years after the discovery of the CMB, its extension rate was revised to be far lower than Hubble's unique number. Later researchers estimated the rate using Type I supernovae as standard candles with steady brightness that may be used as a solid estimate point. Approximately 67 kilometers per second per megaparsec was the expansion rate derived from CMB estimations, while 74 kilometers per second per megaparsec was the expansion rate derived from supernovae estimates. What does this discrepancy actually reveal about the pace of expansion of the universe? Did you realize that individuals have known about this issue since the 1990s? Since then, scientists have been aware of or have conjectured that there may be an issue with the conception of the expansion of the universe, the estimating methods, or the assessment of the CMB. There are significant ramifications of this strain, suggesting that key elements of our possible universe interpretation may be incorrect. Scientists call this disparity between the several predicted upsides of the expansion rate the SAA pressure or Hubble pressure. There was a protracted period of confusion among experts. Since it started working, the James Webb Space Telescope has provided scientists with amazing information that may help them solve the problem of the rate of expansion of the universe. Systems that are so old and advanced that their development should, in theory, have started before the Big Bang are appending conventional astronomy. The greatest urgency in contemporary astronomy is now discussed by scientists instead of flaws or estimation contrasts. Not only is the growth rate a potential error, but the very concept of development or the Big Bang itself is under discussion. Photographic networks offer proof of a reality that is entirely apart from our long-held beliefs. The SAA issued the initial caution. Experts who still hold on to antiquated notions now have to consider whether or not we truly understand the universe. Many researchers explore space in fear, having finished assimilating what they find, and stand on the rubble of their labor of love. The scientific emergency requires us to take stock of what we truly know about the universe. To answer to this, we need to be aware of how science functions. Researchers use a complicated network of precise data, logical reasoning, and numerical models to go from the broad to the explicit, hypothetical. Their knowledge is derived from a mix of observations, anomalies, experimental results, and theoretical analysis. These are concepts and constructs rather than conclusive discoveries, as the word hypothesis itself suggests. Our only trustworthy sources of information are the images that telescopes produce, the radiation and sound waves that radio telescopes record, and the latest information from neutrino estimating systems or gravitational wave detectors. Today, the James Webb Space Telescope has given us an instrument that can dissect the most famous light into its individual frequencies and examine it in remarkable ways. In addition to their mass and number of stars, Webb can identify the most prevalent elements present in worlds that existed prior to 13 billion years ago. It can replicate a world's shape and development as well. Whatever the case, Webb might be flawed too. For example, it cannot reliably tell us if we are looking at worlds or dark holes with enormous accretion circles that shine as brightly as a universe. Modern science has long rejected optional explanations and embraced a vast array of alternatives as insights, and we must acknowledge this truth. Research has been confident in its correctness for a long time. As has often happened in science, the latest discoveries from the James Webb Telescope are important signals to replace speculation with new knowledge. Right now, researchers are making progress. Many analysts find it difficult to offer new insights, and the most recent findings are too startling. The latest discoveries challenge the foundations of modern physical science and worry a lot of professionals. Isaac Newton's research from the 17th century is still the foundation of most physical science courses today. For hundreds of years, his principles of motion and gravity served as the foundation for our actual knowledge of the cosmos and our present environment. On Earth, Newton's laws describe how things evolve under normal conditions. However, in space, his theories needed to be developed, which Albert Einstein primarily accomplished at the start of the 20th century. Einstein's groundbreaking theory of relativity, which was published in 1905, completely changed the way we perceive the world by demonstrating that all of them are similar and reliant on the development of the eyewitness. He developed this idea further in his 1915 general hypothesis of relativity, which included numerical evidence of gravitational peculiarities in light of the bend of space-time by masses such as stars or universes. In many areas, Einstein's principles and theories were applicable, but he also recognized their shortcomings. Despite his desire to imagine a world equation, he was unable to do it because he understood that his theories would never be sufficient to describe the cosmos. No other specialist has thus far been successful. Where's the step? The location is fascinating, isn't it? Famous American astrophysicist Michio Kaku said at a symposium that a Nobel Prize would undoubtedly be awarded for solving this puzzle. Why don't we examine whether the problem is with our telescopes or whether researchers have missed possible miscommunications? Dark matter and dark energy are the most likely culprits for the cosmic emergency's true causes. Although neither has been directly detected, and their existence has never been established, our current models of the universe contain the idea that dark matter and dark energy make up about 95% of the cosmos. Different explanations for the dynamics of systems and the evolution of the cosmos are necessary since they might not exist at all or have characteristics that we do not yet comprehend. The evolution of dark matter and dark energy throughout time, perhaps exhibiting some form of intelligence, is one notion. Gravity is an additional concept that ought to be tested. This capability has not yet been demonstrated to generate interest through space-time bend or mass. In any event, we cannot completely rule out the idea that the gravitational force between objects is due to some unanticipated property of gravity or that it is caused by another influence. Einstein is widely recognized for having developed the concepts of the space-time arch, which have been confirmed by experiments. Over time, a few characteristics have been determined to be infinite constants in cosmology and astronomy. Our constant pursuit of knowledge and understanding has always been a defining feature of the study of the cosmos, from the first human inventions that allowed us to see the stars to the most recent space telescopes that reach the ends of the universe. Every theoretical breakthrough and every discovery has produced new data, and experiments have validated long-held cosmological theories. As a lighthouse of our rational advancement, the James Webb Space Telescope, JWST, holds the potential to transform our knowledge of the universe's beginnings and development. JWST, which was launched with special capabilities, is poised to explore the depths of reality like never before and represents a breakthrough in observational space science. One of JWST's main objectives is to study the cosmic microwave background, CMB, radiation with unprecedented power. The CMB, sometimes known as the glimmer of the Big Bang, offers a view of the cosmos only 380,000 years after it was first observed on Earth. This artifact radiation conveys the fundamental conditions of the universe, including temperature changes, which are necessary to understand the evolution of planets and large-scale structure. A continuous issue with proposing a slower rate of cosmic expansion is the error in the Hubble constant's deliberate upsides, also known as the Hubble pressure. Cosmological tests and Type I supernovae sightings yield a higher value. The tension suggests that our understanding of the mechanics of the expansion of the cosmos may still be lacking, or there may be holes in our current theories. Beyond the Hubble pressure, JWST may also help unravel other cosmic mysteries, like the nature of dark matter and dark energy. Although these intricate elements are believed to comprise the vast majority of the universe's mass-energy content, their existence is still indirectly generated by gravitational impacts rather than being directly witnessed. JWST's capacity to concentrate on the distribution of matter and energy over cosmic history may offer vital new information about the properties and development of dark matter and dark energy. Furthermore, JWST offers a brief window into expansive stories that were already far in the future through its observations of celestial populations and distant cosmic systems. Stargazers can use the light from extinct worlds to trace the evolution of stars and cosmic systems across billions of years. The mechanisms underlying the early universe's formation are also revealed by these findings, which aid in our understanding of the structure of cosmic systems. The telescope's sophisticated technology, including its configuration of spectrographs and infrared locators, allows researchers to examine the material structure of far-off objects in remarkably fine detail. The overflowing of elements like hydrogen, helium, and heavier metals in historical star-forming locales can be measured by JWST, which can help us understand the cosmic history of substance. Establishing models of celestial formation and understanding how the characteristics of universes have evolved over millennia depend on these facts. Among JWST's most interesting capabilities is its capacity to detect and describe exoplanets, or planets orbiting stars other than our local planet group. The feeble infrared light that these far-off worlds emit allows JWST to examine their atmospheres and search for tenability or possibly life. Our efforts to find possibly livable worlds and comprehend the variety of planetary structures throughout the universe have advanced significantly with this capability. In addition to its rational goals, JWST seeks to exhibit worldwide coordinated effort and mechanical development. The international endeavor to push the limits of space exploration was highlighted by the commitment made by space organizations such as NASA, the European Space Organization, ESA, and the Canadian Space Agency, CSA, to the telescope's development. Modern optics tailored for infrared sensitivities and a sophisticated sunscreen that shields delicate instruments from sunlight are only two examples of how JWST embodies years of research and design experience. Launching JWST has not been without its challenges. JWST, which was initially conceived following the success of the Hubble Space Telescope, had unique difficulties, financial requirements, and delays that put the determination of the scientists and specialists involved to the test. JWST successfully launched on an Ariane 5 rocket in December 2021, proving that persistence and creativity were the winning factors. JWST is ready to go out on an unprecedented exploration mission. It is currently in its planned orbit close to the second Lagrange point, L2, which is about 1.5 million kilometers from Earth. Unlike its predecessor, Hubble, which runs mostly in bright and invisible frequencies, JWST's infrared capabilities allow it to see through dense residual clouds and find objects that optical telescopes cannot see. Across a broad frequency range, this unique perspective offers a thorough view of the universe from close infrared to mid-infrared districts. The first light observations from JWST are eagerly awaited by the scientific community, since they are anticipated to provide a plethora of new data and insights on significant cosmic questions. JWST's observations will impact our understanding of astronomy, cosmology, and planetary science for years to come, from examining the circumstances of the early universe to concentrating on the environments of exoplanets. JWST will provide high-resolution photos and spectra of astronomical objects, allowing astronomers to focus on anomalies from star configuration in close systems to the emergence of supermassive black holes at the centers of distant universes. Because of its exceptional clarity in settling minute details in galactic objects, JWST will give vital information to test and refine theoretical models of cosmic cycles. Additionally, JWST observations will advance our knowledge of the life cycle of stars, from their organization in dense atomic mists to their possible destruction as heavenly remnants or supernovae. By monitoring star-forming districts and heavenly nurseries in many systems, JWST will provide insight into the processes that drive star formation and the impact of the environment on heavenly growth. The development and exploration of universes further supports JWST's logical mission. JWST will examine the basic properties, constituents, and intricate structures of systems across infinite time in order to trace the evolution of cosmic formations and their progression into the various clusters of universes seen in the cosmos today. These observations will provide clues about the processes that shape cosmic systems, including very massive black hole development, feedback mechanisms from star formation, and interactions. Beyond conventional astrophysics analysis, JWST can answer basic concerns about the universe's origins and the concept of space-time. By studying the migration of dark matter across astronomical scales and witnessing gravitational lensing impacts, JWST will advance our knowledge of the broad scope building of the universe and the hidden material science that governs its structure and evolution. Multidisciplinary research projects, including the Hunt for Extraterrestrial Intelligence, SETI, and the investigation of the structure and sustainability of planetary systems will benefit from the telescope's observations. One of humanity's most pressing problems will be addressed by JWST. Are we alone in the universe? By analyzing the intricate syntheses of alien environments and looking for biomarkers characteristic of life, this will be achieved. Furthermore, JWST's contribution to motivating next researchers, specialists, and space travelers is the most significant item. People will be inspired to seek jobs in STEM fields by the telescope's amazing discoveries and creative accomplishments, which will enthrall people worldwide. JWST will continue to inspire curiosity, creativity, and a love of learning for many years to come, leaving a permanent legacy of logical achievement and study. As it begins its primary goal to uncover the mysteries of the cosmos, JWST stands as a testimony to humanity's persistent spirit of inquiry and discovery. From its cutting-edge machinery to its aggressive, logical goals, JWST is a success of international cooperation, mechanical innovation, and logical ingenuity. JWST will broaden our horizons, enhance our comprehension of the universe, and inspire the next generation to keep pushing the limits of knowledge with each new finding and observation. Ultimately, the James Webb Space Telescope is committed to revolutionizing our knowledge of the universe and providing new insights into its beginnings, development, and salient features. By stretching the limits of observational space science and developing our creative capabilities, JWST is a benchmark of logical advancement and a testament to humanity's curiosity, constancy, and mission for knowledge. In anticipation of the discoveries that lie ahead, JWST is ready to unravel the secrets of the universe and encourage next generations to discover the wonders of the cosmos beyond our wildest fantasies.